That talks a little fast, okay?
I haven't seen you in a while.
What a difference from your ready to get
Anytime.
us on time.
Yeah, sure.
Okay.
Yeah, no problem.
Welcome to E&E seminar. I am filling in today for Michael Louie. So I would like to thank our snack bringer, Bruce Traveler. Thank you. And I also will be passing around attendance sheets. If you are a visitor, we would love to have your name on here. And for students who are enrolled in the class, it's important that we account for you being here. There is also a snack sign-up sheet going around. We have 1 day left available at the end of April if you are so inclined to provide snacks for our group. Sorry. So I'm really pleased to have the opportunity today to introduce our speaker. He is a physics education researcher with a background in physics who started that trajectory as a postdoc at Kansas State and recently joined us here at Purdue University across the departments of physics and astronomy and curriculum and instruction. He's focused on transfer and learning and problem solving, and more recently, which we'll hear about today, the implications of visual cognition for problem solving in STEM. So I hope you'll join me in a warm welcome with Professor Sanjay Rosello.
Well, thank you all. Thank you, Alison, for that introduction, and thank you all for having me. It's a pleasure to be here amongst various engineering educators to talk about some of my work. Michael Louie asked me to say a few words briefly about my career trajectory, because he said graduate students typically like to hear about career paths. So I just wanted to say a few things. I started off actually without any formal background in education, either physics education or any kind of education. I got my degree in solid state physics and a master's in engineering, so I do have a little bit of engineering background. And then went off to do a postdoc, as Alison mentioned, in physics education research. So that was my career trajectory. And I often find myself amongst people who know a lot more about education than I do. And so I'm still trying to learn and make my way through all of this, the field of education and learning about theories of learning and so on. I'll be talking to you today about some of the work I've recently gotten involved in. It's work that started off about 5 years back. I was at Kansas State University before coming here, and I ran into a cognitive psychologist who was studying visual cognition. And he and I talked a little bit, and I had always been interested in eye tracking and looking at how people look at problems and look at tasks and try to think about what implications that might have for what we can learn about problem solving. And we talked a little bit, we threw a few ideas back and forth, and we had a graduate student who was really interested in doing this. I didn't have any background in this. She didn't have much background in this. He knew a lot about it, the cognitive psychologist. So we got into this, did a few studies here and there, applied for some funding, fortunately got it, applied for some more funding later on, and here we are. I'd like to say a few things about what the term problem solving. A lot of you in engineering education, as well as in physics education, when you think about problems, you think about real-world problems, you think about problem-based learning, a lot of interesting stuff, a lot of stuff which involves real-world applications and connections. Unfortunately, the problem solving that I will be talking about is very mundane compared to what you are all studying here. So I apologize for that, but that's what I do. There's been some concerns or some comments which I've received in the past about this work say, well, what you're really having students do are not really problems, they're tasks or they're questions or whatever. So you might want to call them whatever label you want to put on them, but basically we are looking at how students use visual information to accomplish some kind of a goal that we have set for them. So with that, I'd like to sort of say a little bit about what I'll be telling you about today. I'll be talking about visual attention in general, just a brief primer on that. And why do we care about visual attention? What factors influence visual attention? There is a study that we did to explore that question. And a couple of studies as to whether we can influence visual attention and how influencing visual attention might impact how students perform on these tasks or problems that we set for them. So first of all, visual attention is basically the process of concentrating or focusing your mental effort to look at a very specific piece of information that's presented to you visually. That's a very basic definition of visual attention. And we need visual attention oftentimes because there's just so much out there. There's so much information out there that we have to zone in or zoom in on a certain piece of that information to actually accomplish something. If we try to incorporate everything that we see, we'll often be left unable to make any progress on any task that we might be presented. So the question then is, why is it relevant to learning? Well, if you think about learning nowadays, and not just nowadays, but it's just been going on for several years now, is that we present students with visual stimulus. Back in the day, we were using textbooks. They still were a form of visual stimulus. We present them with computer-based graphics, animations, all kinds of stuff that they have to deal with. It's all visual. And oftentimes, there's just too much information out there. And the visual system has limited ability to process information. And oftentimes, elements compete for information. So if you look at this computer graphic right here, you might find that there's a lot of information out there. There's the projectile trajectories which are shown to us, shown to the students. There's information in numbers with various parameters. Let's see what. And they have to attend to all of this information, decide what is important, what is unimportant, and make progress. Similarly, with the circuit diagram over here, there's a lot of information as well, and they've got to decide what is relevant, what is irrelevant, and so on. So if we know more about visual information, we might be able to use that knowledge to design images and graphics which can facilitate learning, as opposed to designing stuff which actually impedes learning. And research has shown that, in fact, poorly designed images do impede learning. So how do we measure visual attention? Well, visual attention is measured using an eye tracker. I know there's an eye tracker somewhere in this building. I've been told that there's some faculty members who do research. Anybody here who does research using an eye tracker? Oh, great. So we probably should talk a little bit more after this at some point. So we are using an eye tracker which is made by SR Research. It's iLink 1000. There are several eye trackers. The faculty member I collaborated with in visual cognition basically told me buying an eye tracker is like buying a car. You can buy $10,000 or $50,000 car, or you can buy Cadillac all the way up the scale. So it's a wide range of devices that are available depending upon your needs and depending upon your budget. You choose to buy one. This is what was there in the cognition lab, visual cognition lab at Kansas State, and now we have one here at Purdue. And the basic idea is to measure the point-by-point gaze, and the idea is the notion that you can measure this, gather this information that has some relevance to learning is based on what's called the mind-eye assumption, which was proposed way back in the 80s by Justin Coppett, who basically said that if you can record the location and the duration of eye fixations, that can moment-by-moment fixations of a learner, that might give you some insights into how they're thinking. So if you're focusing on something, you're probably thinking about it. That is the assumption that is underlying this. Now, there have been more recent studies on mindless reading and so on, which challenge this assumption a little bit. But in this particular case, we're looking at students who are focused on solving a particular task. And so we assume that what they're looking at is what they're thinking about, tells us something about what they're thinking about. So that's the underlying assumption for this work and a lot of the work that came before this. Now, there's been a lot of work done on expert-novice differences on visual attention. So there's a host of work out there going back several decades. And the earlier studies started with reading, looking at learners with reading issues or difficulties with reading, and trying to look at the eye movements and trying to understand what might be different about learners who are able to read easily versus those who have difficulties with reading. But more recently, there's been work on looking at images, which is kind of the domain that the work that I've been doing is focused on. And so some of the results tend to converge on the idea that experts tend to focus more on relevant features of a diagram. So for example, while studying the locomotion of a fish, you find learners fixating. These are sort of this dot here, white dot is an example for fixation. The size of the dot tells you how long they're fixated on that, and the location of the dot tells you where they're fixated. So they fixate on things like the fins of a fish if they are thinking about locomotion of a fish. There's been research on comparing expert-novice differences on looking at paintings and where they look at trying to decide whether a painting is worth its value or not and the quality of a painting. There's been research on looking at chess players. So it's been found that expert chess players and novice chess players look at the chessboard very differently. If you're a novice chess player, you tend to look at the pieces, which is what this person right here on the left is doing. They're looking at the various pieces on the chessboard. Whereas if you make a lot of fixations on these different pieces. But if you are an expert chess player, you are not making as many fixations apparently, and you're fixating more on the path or the points between the locations as opposed to the locations themselves. And that might have to do with the way in which experts and novices think about movement of pieces and the paths that these pieces can take on the chessboard and so on. So there's been a lot of work done in a domain which is other than science or physics per se. Well, I guess locomotion of a fish can be considered science. But more recently, we've been looking at vision attention in more traditional STEM domains such as biology, chemistry, and physics, and so on. And there was a study done. I'll just talk about a couple of studies because there are a host of studies out there, but a couple of studies here. This was a study done with pre-service teachers in biology, chemistry, and physics. And each of them was presented with problems in each of the three disciplines. So essentially, you had each teacher solving a problem in each of the three disciplines. And these problems are taken out of the New York Regents exam just because they wanted to look at tasks which have been vetted and validated quite well before presenting them to these teachers. And what they found was that if you're a biology teacher, so this is an example for biology teachers, eye fixations. So she's looking at a biology problem right here, and you can see there are very few fixations that the person makes and very few transitions between different zones. So there's the question information up here, there's a multiple choice here, there's the diagram there. I couldn't get a better diagram, I'm sorry. I looked at the publication, this is the best they had on there. So I don't know why. I was hoping they would have provided a much cleaner diagram to show the data, examples of the data, but this is what they had. So in any case, this is a biology teacher looking at a biology question. You see very few fixations and very few transitions back and forth between what are called saccades, between different areas. Now, then she goes on to solve a chemistry problem, and you can see many more transitions, many more fixations. And again, in a physics problem, it's different. So when you're in your area of expertise, you tend to make fewer fixations, and you make fewer transitions or saccades back between areas. Another example here is with going forward. There we go. So another example here is with students looking at problems on electric circuits. Now, this might be of relevance to those of you in electrical engineering or engineering in general. And what we found here was that, what these authors found here was that if you're a learner who's a novice, who typically is struggling with this solving a circuit problem, you will tend to look at the individual components of the circuit. You look at the battery, you look at, well, this person did look at the battery, but you look at each of the individual resistors. But if you are if you're more of an expert, you have learned a little bit about loops and nodes and paths of currents, etc. You tend to look more along the path which the current actually might take. And so there's a difference there in visual attention between these two groups. Then moving on to another study which was done by Phil and Mestre here. By the way, Jose Mestre is from Urbana-Champaign, and he'll be visiting here next week giving the physics colloquium on some of his work. And this work as well as some of the work that he's been doing. So they looked at what is called change blindness. So if you're shown a diagram and you're asked to look away and asked to look back at the diagram, and something in the diagram has changed, the question is, can you detect the change or can you not detect the change? And what he found was that experts were more likely to notice the change if it affected the solution to the problem, if it was a relevant piece of information that was changed. So for example, the difference between this diagram and this diagram is this particular string that's attached to the mass at the top. And now that is relevant. It's a minor change if you think about it visually. There's so many things out there, and this is just one minor line that goes across. And it's relevant, so experts tend to notice that, but novices will just ignore it because they tend to focus on other things, perhaps the other features such as the size of the blocks, the shading, and so on. So again, all of these studies tend to converge on the conclusion that there's a difference in visual attention, and the experts tend to focus on information that's more relevant to solving the task, and novices don't. So having looked at all of this, we said, well, let's look at certain specific tasks in a physics course, and let's see whether there's a difference. So we looked at tasks which were presented to students. These are taken from, some of these are taken from a commonly vetted test called the force concept inventory, which is a commonly given inventory to measure students' conceptions of force and motion. It was developed in the 90s. It's been given to thousands of students across in different schools and universities, and it's often used as a measure to assess whether students have a Newtonian understanding of force and motion. So we were looking at this from the point of view of visual attention. So this is an example of a question, and the question we were asking was, how did the visual attention differ between novices and experts on these kinds of tasks? And this is an example of a task where there are two balls along a track, and you're asked at what points in time are the two balls moving at the same speed. That's essentially the task. And we wanted to look for differences in attention. And we did this with a group of participants. There were 9 physics graduate teaching assistants and 30 introductory psychology students who had physics in high school but no college physics. We wanted students that had a little bit of physics in high school just because some of the terms, in some of the questions, there were terms which were not necessarily understandable. Not all of the questions were from the force concept inventory. Some of them had words like potential, energy, and we wanted to have students who actually had seen that word before, had seen some of the terminology before they actually looked at these questions. And we compared them. And initially we thought, well, the graduate TAs are going to be all experts and they're going to get everything right, and the introductory psychology students will get everything wrong. But it turned out that was really not the case. We couldn't pre-categorize them as experts and novices. We actually found out that a better way to look at the data was looking at those who solved problems correctly versus incorrectly, as opposed to thinking of them as experts and novices. So these were the materials, as I said before. There were 10 multiple choice conceptual questions in various topics, and some of them are from the force concept inventory, some of them are from other inventories based on circuits and so on. Each problem had a thematically relevant region. So for example, in this problem, which is a roller coaster problem, you find that you really should focus on your aspect. The question is, if they both start at the same speed, these two roller coasters, and the track is frictionless, how do their speeds, final speeds compare if their initial speeds are the same? Well, the answer is that you really shouldn't worry about the shape of the track and the bumps and the kinks of the track. What you really should attend to is the positions, the initial and final positions, actually the vertical position of the objects. So this is sort of the relevant area here, which looks at the positions ignoring the track. And there were other problems as well of this kind. And we basically presented these problems to students. This is another problem as an example. It's a skier going down a slope, and the students are asked to rank the changes in potential energy. And the relevant area here is, there are 2 areas of interest, one relevant and one irrelevant. The relevant area, or we call expert-like area of interest, AOI, focuses on the vertical heights, and the irrelevant area focuses on the slopes. So again, we want to look at where the students attend to, and we looked at the dwell time. We compared the dwell time for the correct an incorrect solver. So our independent variable here is the correctness of the answer, which is a little unusual because usually you look at correctness of the answer as a dependent variable. But it's independent because we are using that to categorize our two groups of students, those who got it correct and those who got it incorrect, and then looking at their visual attention to see how they compare. And this is what we found. We basically found what we would expect from previous work is that the correct solvers tend to focus more on the expert-like area and less on the novice-like areas. And the novice-like areas are typically areas which are based upon some kind of a misconception that students might have on that particular question. And on the incorrect solvers, there's again a difference between the two. And they tend to focus more on the novice-like areas than the expert-like areas. So there was a clear confirmation of many of the results that other studies have gotten with this. So the question then is, what can we do about it? So this is another example of this actual data from this study. So this is the eye movements of an incorrect solver looking at this problem. There's a problem of a position versus time graph, and the question is, at what point in time are the two objects represented by the two graphs moving at the same speed? And so if you wanted to think about this, you really have to think about rates of change of position, which is the slope of the graph. But what the incorrect solvers typically tend to focus on, as you can see here, they tend to focus a lot on the points of intersection, which is sort of guided by their the naive understanding of what the graph represents and what speed means. But also it's the visually salient portion of the graph. And the correct solvers tend to focus on the slopes of the points where the slopes of the two graphs are the same. So the question is, what can you do about this? Is there a solution to this? Can we redirect visual attention and change students' performance on these tasks and other tasks which have a strong visual component to them? We all know that, this study and other studies have shown that that eye movements are affected by cognition. So if you think in a certain way, you look in a certain place. But the question is, if you change where people look, can you change the way they think about things? That's the thing we are after. So what we decided to do was we decided to ask the following questions. We said, can short duration visual cues? We know how experts look at problems. We have the eye movement information. We have looked at eye movements of students who got these questions, who solved these tasks correctly. The question is, if we are able to make novices look at these problems in the same way, move their eyes in the same way, will they begin to think about these problems differently? And it's not sufficient that they solve the problems that we give them differently. Can they transfer this ability to solve problems to another problem which no cues have been provided? So that was sort of what we were looking at. Can they change the way they think about these problems, and can they transfer this thinking to a different set of problems which have the same underlying concept but are very different in terms of surface features? So there's some empirical evidence to suggest that what we were trying was possible. Otherwise we wouldn't have gone that route. So there's been actually a lot of work done on visual cueing before we got started. It's been done in other domains. And it's often been done in domains which relate to, often been done on tasks which involve comprehension and recall as opposed to problem solving and transfer. A little bit on problem solving and transfer, but not as much. So this is one, a study that was done by Deconing and colleagues who looked at the use of spotlight cues. So if you're trying to learn about the cardiovascular system and how blood flows from the veins through the heart and the various auricles and ventricles of the heart, etc. Can you learn that better if you're given cues? And well, clearly, if you're given cues with spotlight different areas of the heart, you will have a better recall of that information later on. And also comprehension and transfer, if you're asked to apply to a different situation. There was work done by Buchicks and Lowe who talked about spreading color cues on a piano mechanism. So this is a piano mechanism, not very clear here, but you can see a portion here is highlighted. That's where the hammer strikes, one part strikes another part. So you highlight that in an animation as the animation is played, and you find that people tend to remember that event much better. much more clearly than they would if you didn't do it, as you would expect. Then there was another study that was done by Chris and Hegarty, and they looked at a cistern. And this is, again, you would expect this to be the case. That is, when you provide arrow cues, that is, arrows which point to relevant parts of the cistern, again, it improved comprehension of the cistern's functional mechanism. And then there's finally this study, which actually was the last one here, which actually was something that was served as an inspiration for what we are trying. It's called the study by Thomas and Yearis. It solved the tumor problem. The tumor problem is a rather old problem, goes back to the 1940s, and basically it was originally used to measure transfer of learning and demonstrate that transfer of learning is hard. That's what the results tended to show. And the problem was basically one where you're given a story about a general who's trying to attack a fortress, and the fortress is surrounded by a moat, and there are bridges that allow the troops to cross the moat. However, the bridges by themselves are not strong enough to bear the weight of the entire the entire army to cross the bridge. So what really needs to be done is you cannot attack the fortress through a single bridge. You have to surround the moat and approach it through different bridges on different sides and converge onto the fortress in order to capture it. That's the narrative that is presented to the learners. And then they're presented with a very different problem. The problem is this patient has a tumor, and the tumor is surrounded by healthy tissue, and in order to attack the tumor, destroy the tumor, you need radiation. They didn't have lasers back in the 1940s, but they did have X-rays. So you have a beam, an X-ray beam, which is really intense, but it will cause damage to the surrounding tissue if it is just a single beam. What would you do to cure the tumor? Well, the answer, which might seem obvious to the researchers who were doing this, was that when you figure out a mechanism to break up that beam into multiple beams coming in from different directions, each beam is weak such that it doesn't destroy the surrounding tissue, the area of the tissue that it passes through, but it converges onto the tumor, and at that point it's strong enough, intense enough to destroy the tumor without destroying the beam. So that was kind of a study which a problem that has been looked at a lot. And what Thomas and Yearis actually did was they provided visual cues. So there was a group of subjects who were given cues, and they were asked to move their eyes along a direction which embodied the solution to the problem. So they had to move their eyes from here to here, here to here, here to here, and so on, all converging to the center. Another group was given cues where they essentially followed a single back and forth path. And there were two other conditions that I cannot recall. But what they found in this study was that those who followed a path which was consistent with the solution to the problem, or those that embodied the solution to the problem, were actually able to solve the problem. Without being told that this is, they're not given the problem to begin with, they were just asked to move their eyes, and then they were presented the problem. So there was some strong evidence there that if we were able to move people's eyes and make them think about things differently. So we decided to sort of try that, and now we look at the theoretical basis for that. There's a strong theoretical basis. The cognitive theory of multimedia learning by Meyer also suggests that if you provide information, if you're able to guide the selection and organization and integration of information, that can help learning. Also, the other theoretical basis for this is the idea of cognitive load. And we talked about earlier how there's a lot of visual information in a person's visual field, and you really need to help them focus on a certain piece of that information. Well, cues might be able to do that because they are able to highlight information, make it visually salient, which directs your visual attention, and therefore you begin to start thinking about that piece of information as opposed to everything else out there which might be capturing your attention. So those are sort of the two basic ideas that were guiding our work. And so we did this with students in algebra-based physics. So these were students who were going on to be life science majors, and not engineers, but other areas of science, not physical sciences or engineering, but biology and life sciences and so on. And this was a design, so we presented each of them with an initial question. No cues were provided on the initial question. And then each group had to solve a set of similar questions. Anytime they got a question correct, they were sent to a transfer question. And on these similar questions, students were in two groups. So there's a non-cube group that were basically given the question, and the similar questions were isomorphic to the initial question. So they were changing slide surface features. So if you think about the ball problem, there's a ball, but then things change about it. The locations of the balls change, but basically it's still the same problem. And there were two groups. The non-cube group did not get any cues on this, where the cube group got cues based upon expert eye movements. And I'll show you an example of those cues in a moment. And then, whenever they got one of these questions correct, they were given a transfer question. They got through 4 of them and it still didn't get it correct. They were sent to the transfer question regardless. So this is an example of the 4 problems we had. One is the roller coaster problem. I've talked about this previously. The skier problem, I've talked about this as well. The graph as well, and this is the ball problem. So you've already seen these problems on various of the slide. But I'd like to focus on the cueing example. So this is an example of cues on the ball problem. If you look at the ball problem here, this is what the student saw. So you can see here, the cues are showing up, asking them to focus sequentially in a particular sequence on various balls. So, they focus initially on one ball, and next, and then one subsequent to that, then they go to the lower ball, and the one subsequent to that, and so on. So this was based upon expert eye movements. We looked at the experts, so the people who got the problem right, that's what they did. So we thought that, well, having students do what the people who got it right did would help them solve the problem. That was kind of underlying assumption here. So this is what we found on the various problems. So there was improvement with the cues versus without the cues, but it wasn't great overall. We found that only one of the problems is statistically significant. For some reason, the roller coaster problem, nobody was actually able to get it correct on any of them. So clearly there, with the cues, they were able to get it correct at a 30% rate. So that wasn't still great, but it was better than no cues. Transfer problem, again, in the ball problem, they got that correct significantly more often than without the cues. But again, improvement, but not marvelous. No, nothing that was really made us feel very happy about this. So we began to think a little bit about this. An example of the transfer problem, by the way, for the ball. So remember the balls were on horizontal tracks. Here, one ball is in an elevator moving at a steady speed down, and the other ball is dropped off a building. So the same situation, the same idea, but just in a vertical domain as opposed to a horizontal situation. So we also looked at the eye movements to see what we found with the eye movements, because we were interested to see whether the cues actually help students attend to the right areas, which is important. And we looked at the eye movement in the expert-like area of interest, which, for example, for the ball would mean focusing on the areas which are between the balls. The novice would mean looking from one ball to the corresponding ball directly below it. And this is what we found. The expert-like, clearly the cube group spent more time on these. The asterisk indicating statistically significant ones at the 0.05 level. The novice-like, again, we find the non-cube people spending more time in the novice-like area, which is what you'd expect. So they were consistent with what you would expect. But the performance differences, which I showed you on the previous slide, were also positive, but not overwhelmingly convincing in terms of the effectiveness of cues. So we began to think a little bit about this. So overall, our conclusions were that they do show promise in some tasks. They can improve performance. They can improve performance in transfer tasks as well. And they do shift attention. However, we find that the results are not uniform. We find big differences across problems. Some problems really good, some not good at all. And we asked students after the interviews over, what do you think these cues were supposed to do? We were not telling students that the cues were supposed to help them, by the way. We didn't tell them the cues are designed to help you. We just said, you're going to see some shapes moving across these problems. That's it. And what we got back from the students when we asked them, what do you think the cues are supposed to do, was rather interesting. Many of them, there were a fair number who thought that, yeah, the cues are supposed to help me solve the problem, or you're trying to give me a hint. But there was also a fair number who said that, I think you're trying to trick me into looking at something. You're trying to confuse me or distract me or something. So, this is what happens when you take students into a psychology lab, right? There's this inherent notion that you're trying to mess with their minds somehow. So that kind of played a role here a little bit in their thinking. But in any event, we decided to sort of move forward and ask ourselves what else can we do to facilitate this. So if you think about our roadmap thus far, what we did was our initial work was focused on looking at visual attention. Then we looked at cueing. Can we develop cues to facilitate problem solving? There was another study on salience manipulations, by the way. We looked at if you change the diagram, let's say you take the graph diagram, and with the point of intersection versus the point where the slopes are the same. Let's say we use luminance contrast to make the point where the slopes are the same really, really salient, visually salient. Does that change their attention? It turned out it didn't. It didn't change it changed their attention, but it didn't necessarily change their performance. Or in some cases, it changed their attention for the first couple of seconds, but eventually they began to go one way versus, depending upon their top-down thinking, that is their domain knowledge and their initial understanding, as opposed to their visual salience. And then they asked ourselves, what else can we do to improve cueing? Because we found that cues show promise, but at the same time, they're not overwhelmingly convincing in terms of improving performance. So one of the things we decided to do was we wanted to redesign the cues, go back to the drawing board, because our cues have been designed using expert eye movements. And so we wanted to actually vet these cues with students. So we actually had students come in and we said, take a look at these cues. What do you think they're trying to tell you? What do you think they're making you think about? And we did that with a whole bunch of students. This was sort of a pilot just to validate the cues. And we found that a lot of the times what we thought were effective cues meant nothing to the students. So we used what the students in our study would find helpful and decided to use those in the next study that we would do. And we also felt that we also decided to give feedback. So, we had told students earlier that we had not told students anything about whether the cues were designed to help them or not. We said, we'll tell them that we are going to show you something which is going to help you solve the problem. And we also decided to tell them when they were wrong. So, not anything more, not tell them why they were wrong or how they were wrong, but just that they were wrong, incorrect, on a particular problem. So this was the first study, this was the second study, and the next study, which I'll just be telling you about, is the third one right here. So in this study, the theoretical background, again, goes back to a framework for visual cueing, which is based upon the multimedia learning theory. And the colleague and co-workers developed this framework. They basically talk about selection, organization, integration, and how cues can facilitate each of these processes. So selection cues basically can help you attend to thematically relevant information. They just direct your attention to the information that's relevant. Organizational cues actually help the learner make connections between different pieces of information on the diagram. And finally, integration cues involve, if you have multiple modalities involved in your question, which we did because it's all visual. We have done a study later where we have audio and text and so on, but in this particular case, we're really not going to integrate multiple modalities. But in any case, that's what the theory framework is. We also went back to looking at some of the early literature on problem solving, and we looked at Olson's representational change theory. And Olson talks about the following processes. Talks about reading and extracting problem information. Anytime you see a problem, you activate your prior knowledge, you encode the problem in a mental representation. In this case, it would be like deciding whether this is a potential energy problem, this is a distance versus time problem, and so on. And then you ask yourself, you don't necessarily do this the way I'm talking about it, but this all happens really fast. Is a solution path apparent? And if it's apparent, then you use that representation to execute a path to the solution. If the path is not apparent, you're in a state of impasse. An example of an impasse is if you're asked to solve the typical 9-dot problem. The 9 dots arranged in a square, and you're asked to draw 4 lines that connect all the 9 dots. And oftentimes, you're in a state of impasse. You try something, you get stuck. You try because you're representing the problem as being confined to a box, imaginary box. But if you go beyond the box, you can actually solve the problem. So that's an example of impasse. And in order to overcome impasse, you need to be either provided new information, which is add some information added to the diagram, or you need to either suppress or enhance existing information. So those are the types of cues. Cues would help do that, which would help you then go back and re-encode the problem and think about it differently. So that's kind of the underlying mechanism we were using, cognitive mechanism, to think about how students might be approaching these problems and how they might be going through this and where cues can help them. And now feedback is another element, which is not a part of the Olson's framework, but it's been found to be really useful. And we are talking about outcome feedback, that is just telling the learner whether he or she is correct or incorrect. And there's been research to show that just doing that is adequate to produce some gains. So this has been shown with English grammar and punctuation and learning of Spanish, learning a second language. You're being told that you are incorrect helps the learner go back and rethink what they were thinking about and figure things out for themselves. So you don't need to do much more. Well, if you did more, you can obviously get other gains. But we didn't want to go that far. We wanted to rely on a combination of cues and outcome feedback to see if that would make a difference. And so in our model here, which I had earlier on, now we have another piece, which is feedback. So once they execute a part of the solution, they are provided feedback. They're told, those in the feedback condition are told that whether they're right or wrong. They're not told why they are right or why they are wrong. They're just told this is incorrect, you were incorrect, or you were correct. Now, it turns out that if you're told that you're incorrect, but you're thinking you were correct, that's a point of cognitive dissonance. That gets you to a point where you say, oh, I thought I was correct. I thought I was thinking about this in the right sort of a way. But if you are told they're incorrect, you enter a state of impasse. So that's an example of impasse. Now, when you get in a state of impasse, if you're in the cube conditions, you can be provided with a selection cube, or you might be provided with another kind of a cube, which is an organizational integration cube. So we didn't differentiate between these cues very carefully, but the idea was that we either want to add more information or we want to suppress or enhance existing information. So the study design involved 4 conditions this time. And so we had students from the same algebra-based physics course, a different semester, of course. And there were 4 conditions. And the 4 conditions, and each of the conditions involved interviews with 50, lasting about 50 minutes. The cube conditions had visual cues. So 2 of them had visual cues, 2 of them had no cues. And the other conditions, 2 of them had feedback, 2 of them had no feedback. So this was a 2x2 design, essentially. The students were again given a set of problems, an initial problem, 6 training problems, and then a transfer problem. So the difference between this study and the previous study was that we didn't send students directly to the transfer problem if they got one problem correct. Because we felt that it was important to see the effect of multiple trials, multiple practice over several problems in order to see the effect of cues and so on. And these conditions were applied only to the training problems. So there were 4 sets of tasks that they completed, and these conditions that I just described about were applied to only the training problems, not to the transfer problem or the initial problem. So the results, this is an example of an initial problem and the training problem. As I said, the training problems are isomorphic to the initial problem. That's an example of the various training problems in the ball problem set. This is the transfer problem. I've shown this to you before. And this is an example of a problem with the cues. So now here, the cues are different from the ones I showed you before, because these cues were based upon validation that we did with students in the pilot study. We actually asked them and said, what do you find useful? And we sort of developed those cues, which in this case highlight the distance between the 2 balls as opposed to the balls themselves. So these are the questions. We wanted to look at the effects of cueing and feedback, wanted to look at the effects of both on the training problems as well as on the transfer problems. And we wanted to also look at the eye movements of the cued students and compare them with the non-cued students to see if there's a difference there. So this is what we found in terms of the 4 conditions. So here we find the training problems, there's not much difference. So you see this particular group, the cue plus feedback group, seems to start out higher than this one, but actually, now for some reason the error bars have not shown up here, but if you look at the error bars, you'll find that these differences, there's no significant difference there. There is also no significant, there is a significant difference at the end, by the way, when you look at these conditions. And they are significantly different from the no cue, no feedback condition. So this is the no cue, no feedback condition. Everybody kind of going at the same rate, not improving much. You're still at about a 20 to 30% rate of correctness. In the feedback only condition, you find a linear improvement as students are going up. And when you go beyond that in the cue condition, the cue condition actually does better than the feedback condition. You find an initial improvement which is rather rapid, but then it sort of stays steady and improves a little bit only. The cue plus feedback condition goes up, and then you might actually be getting close to a ceiling effect of that because it goes up quite high. If you look at it by problem set, this is what we found. Again, we find that in each of the problem sets, the cue plus feedback condition does significantly better. And they're all statistically significant now with the cue plus feedback being given. And in this case, the cue only condition also does better significantly for the ball problem, which is similar to what we found earlier. The feedback, on the transfer problem, again, we find good improvement, except for the roller coaster problem. It's not statistically significant at a 0.05 level. But on the others, it is. The cue plus feedback condition is statistically significant on the transfer problem as well. Now we wanted to look at the reasoning provided by the students. Obviously, the correctness was determined not just by the answer, but the combination of the reasoning and the answer. To be rated as correct, they had to not just tell us what the right answer was, but also explain to us why that answer was right. This is important because you don't want people to be giving you the right answer just because they've seen something. They should be able to tell you the physical mechanism as to why it's right. So we monitored what the reasoning was. So this is what we find for the feedback-only condition. We wanted to look at the number of explanations that were given. So if you look at the feedback-only condition, you see these graphs, and each of these graphs represent different kinds of reasonings provided. So what we find here, the overall gist of this graph, is that there are several different reasons. And the green one here, which is the change in height, the dark green one, is the correct reason. And you find that that reasoning actually is the one that is most prevalent. But let me get back to the mode, which is the right mode here. But you find that the other reasoning doesn't die off really fast. It takes a while to go down. That is referring to the slope of the graph. If you go to the next case and the one after that, you find that in this particular case, the cue plus feedback condition, the change in height becomes really dominant as a reasoning very quickly. And there's not this back and forth, but people change their answers and reasons back and forth between different conditions. So when you provide cues and feedback both, they tend to converge on an answer really fast. And it tends to limit the back and forth transitional states between different reasons that they might provide. So let's look at the visual attention of the learners. So when we talk about learners, what we mean are people who got the initial problem incorrect and the transfer problem correct. What did they do? I looked at their visual attention. So here are the learners with their initial problem correct and their transfer problem incorrect. Let me get this. Okay, so if you look at this graph, they all started out, this is the amount of time you spent in the thematically relevant area, which is the correct area. So for example, in the bot problem, it will be the area which is between the balls, the horizontal distance between the balls. And what we found here was that they initially started out spending very little time in that area because they're not included on the initial problem and they got it incorrect. So clearly you expect them to spend very little time there. But when they went to the transfer problem, they both ended up spending more time in that area, which is what you'd expect because you got the transfer problem correct. That's just consistent with what we've seen before. So that's not surprising. So that's basically this change from initial to transfer. They've gotten it incorrect, and now they're getting it correct. So obviously they're spending more time there. But if you look at the initial problem only, you find that there's no difference between the acute and the non-acute group. Obviously not, because neither of them are acute, right? They don't see any cues of the initial problem. So you don't expect them to be any different. But what's fascinating here about this is that the non-acute group, that is the blue line, ends up spending more time in the thematically relevant area on the transfer problem than the acute group. So that's counterintuitive. because the question is, why would the group that we cue to spend time in a particular area actually end up spending less time in that area on the transfer problem? So to understand that, we need to actually look at the progress going from the initial problem to the transfer problem, which is over here. So we find that they both started out initially incorrect. They both ended up correct on the transfer. But let's look at the trajectory. We look at the cued group. The cued group actually makes a lot of improvement and then pretty much doesn't need to work very hard to get the transfer problem correct. But if you look at the non-cued group, they are making improvement, and in the end, they're going to still make quite a significant improvement to get the transfer problem correct. So in other words, they've got to spend a lot of time attending to that region in order to extract the relevant information from the relevant region. So what we're seeing here is that the cued group had more practice over time because it had been given cues in extracting the relevant information, and it therefore got more automatized in extracting that information. So that we thought was an interesting aside, not just in terms of the performance, but also in terms of the visual attention. Learners tend to get more automatic about extracting information once they've been cued. They don't just are more likely to get it correct because they're more automatic about it as well. So just to summarize, we found that a combination of visual cues and feedback help in improvement in both transfer and as well as a training problem. And there seems to be a connection between looking at their thematically relevant features of the diagram and answering the problem correctly, as we've seen before. But more interestingly, on the transfer problem, they actually spent less time than the non-cued group, which was fascinating to us at least. So we have some evidence that cues help students develop automaticity in extracting information from the relevant area. And so the question is, where do we go from here? So this is the kind of where we are right now in looking at cues and feedback. There's been some studies we've done on looking at Gestalt grouping principles. We kind of want to come up with an underlying theoretical basis for designing cues. So you don't have to go through the process of developing cues each time for a new problem and interview a bunch of students to figure out whether the cues work or not. We want a theoretical framework to allow us to design a cue with a relative level of confidence that will say, well, this cue is going to work because it is based on certain principles. So you're looking at Gestalt grouping principles as an underlying framework for that and trying to see whether that will help provide us some guidance. We are also looking at adding more information. So for example, why just a cue? Let's provide full solutions and see whether they make a difference. And we have done a study of that, which has some interesting results. The question is, the goal is online learning. Will this work when it's provided online? We did a study on that, and we had some interesting results. The gist of it is that unlike the lab study, which I just showed you, where the cue condition does better than the feedback condition, when you present this information online to students working at home or wherever in an online environment, they tend to pay more attention to the feedback than to the cues. The cues do help, but not as much as the feedback does. And some of it might be due to the fact that they are not as used to looking at cues in the other online homework systems that they typically use in their other courses. Cues are rather strange for them. But feedback they're used to getting in most online courses. So we think that might be the reason. We also look at delayed transfer. So we bring these students back 2 weeks later and present them with the same problems. Are they able to, do the cues still have an effect? And we have found some evidence that they actually do. And then the other last study which is currently underway, actually collecting the data, analyzing it, is if you provide other modalities, audio and textual information, in addition to cues, will that make a difference? And we have some interesting counterintuitive results there, which we are still trying to sort. So with that, I'd like to thank you all for your attention, and I'll be glad to take any questions. Yes?
So I have a question that goes back all the way back to slide 14. When you were looking at,
Sure.
you were looking at the expert novice and looking at their patterns.
Okay. Right here. Okay.
Yeah. And you wanted there, so there was something you said that made little bells go off in my head
Okay.
about that the ones that were looking at things incorrectly, the novices, that some of the patterns were reminiscent or perhaps indicative of misconceptions they might have had. So I wondered if you were able to, if there was enough data to be able to group these and say, well, people who had this kind of misconception looked at here, or these people that had this kind of misconception looked here. If there would be any way to link those and possibly maybe use that as a diagnosis for different misconceptions students have.
Yes, actually, so what we found, so in most of these problems, there's typically one predominant misconception. And so, and that was often associated with the novice-like area. So what we did find when we asked students their reasoning, so they were not asked not just for giving us the answer, but also their reasoning. We did find evidence of the fact that the reasoning was based on an incorrect or a misconception. And so they're looking at a certain area was based on that misconception.
Interesting.
So yeah, we did find that evidence. I might not mention.
Pardon me, Professor, did anyone find a hat and coat in this room?
Hat and coat.
No?
I
That
don't.
doesn't look like it. I was
Yeah.
right here. Okay, thank you.
So, other questions?
You may have time for maybe one more.
Sure. Yes.
Related to that, when the students are being taught about the problem in the first place, are you actually teaching these, or are you trying to monitor how much they need coming into this place?
So they had completed coursework which covered the relevant material.
But that was by other teachers.
That's right. Yes.
Yes. I think there's an issue there, because if you're going to teach it, and then you probably need to spend some time telling the students what are the machines, so they don't.
You mean before they come
Yeah.
to this? Oh, well, so our goal here was to figure out exactly whether, so we knew that many of the students have misconceptions even after standard instruction. So that's been established by other researchers. So the question is now, there are going to be some who have those and some who do not, some who figure out how to do it correctly. The question is there a difference in visual attention between those? And if there is, can we provide visual cues to shift that attention, and will that help them address or think about things differently so they no longer demonstrate that
If you
misconception?
explain what the misconceptions were to these people
Before we did the study, but then that would defeat the purpose, right? I mean, the point was to provide visual cues and see if that was effective. If you told them what the answer was, then how would that?
You wouldn't tell them what the answer was. You would tell them what the process was, to try and see if they even understood what you were saying about why it was incorrect. Because maybe they still didn't get it.
So, but then we would, I mean, if you explain it to students in advance, right, versus, and then provide them with cues, then the effects that you measure. So I guess you're saying before even the initial problem? So a larger percentage will probably get it right initially.
That's right. And that, to me, that's your ultimate goal. So if you're trying to take someone who's not trained in education,
Right.
give them a few good pointers about here's what you do as a class.
Right.
Spend some time on each different area and tell what the misconception is. So maybe that will help the total group.
Yeah, it might have improved the initial problem performance a little bit. But yeah, I don't know how it would affect the effective cues. I don't know. Yes?
I think what she's asking is if you just tell somebody that this misconception is a misconception, that doesn't tend to correct their understanding.
Right. I figured that.
And there's also this issue that Sanjay's presented about transfer. And you have long-term transfer issues if you tell them these issues. If you tell them. But trying to clarify what you're saying.
Oh.
Yeah, I mean, I guess you could provide some kind of instruction prior to the initial problem. So, and then, that might bump up that initial percentage. And then the question is,